Okay, so here we go. Oh, wait. Yeah, here it is. I'm asking you just to believe this. You know what we were doing? I'm just asking you to believe it. I'm not going to justify it for you. I'm not even going to pretend to justify it. I'm just going to say believe it. And what you guys were practicing, many books call it the fundamental theorem of calculus. What's that?
That was the second.
Oh, so our book calls this the second fundamental theorem of calculus? Then this guy here is the first fundamental theorem of calculus? Because there's essentially two equivalent parts to the fundamental theorem of calculus. That is, there's two parts to the fundamental theorem of calculus that are logically equivalent to each other. And it kind of doesn't matter what order you present them in, and it doesn't matter how you present them. They both essentially mean the same thing. So the one textbook I used to use called this the first fundamental theorem of calculus, and it called this the second fundamental theorem of calculus. But you're saying that our book does it the other way, and that's fine. But anyway, here comes the other fundamental theorem of calculus, and I'm going to have you guys sneak up on it by doing a bunch of problems. So here, let me pass out this Xerox, and then you guys, we're going to do some problems together, and in so doing, we'll sneak up on that whole fundamental theorem of calculus thing. What's that?
High coefficient of friction between the fingers.
Extremely high. Yeah, I need to. You were telling me. Who's telling me that someone uses rubber finger thingies? Yeah, I might do that because I'm getting tired of using water to gain that extra traction necessary for passing out paper. Yeah, little rubber thimbles. Anyone ever use a thimble? Yeah, I've never had to use a thimble in my life until I had to sew up my backpack, and it was just really hard to get the needle through the canvas, and then I used a thimble, and I felt like such a little homemade shape. I think I shorted it.
She also does the thing, so.
Okay.
She does.
What? Oh, that's right. This is if your sheet exists. Yeah, like you were like a nothing, Okay, here we go. The second fundamental theorem of calculus, or as our textbook calls it, the first fundamental theorem of calculus. Sometimes you have functions that are actually a summation of a rate. That is, if I happen to know the formula for the rate at which water enters my reservoir, then if I wanted a function that tells me how much water is in my reservoir, I would need a function that adds up or sums up the rate. And that would require me to have an integral. So you get this situation, and look at number one, where you can have a function which is defined as the integral of another function. Okay, so look at that there. That's number one. If I want to find f of 4, what do you suppose that's going to entail? Thank you. I'm going to plug in a 4 for x. That is, I've got a function where what I'm plugging into the function ends up being what I plug into one of the bounds. That is, if this is a function telling me how much water is in my reservoir on day x, then the amount of water in my reservoir on day 4 is going to be the integral from 1 to 4 of radical t dt. You see what I mean? So you're going to have functions that require you to plug in for the bound, because that bound is going to tell you, how many days you care about for your reservoir, or whatever it happens to be. Well, let's go ahead and complete this problem. T to the 1/2 power, the antiderivative of t to the 1/2 power is going to be t to the 3/2 power, but then I have to divide by the new exponent, divide by 3/2, which is the same as multiplying by 2/3. Is there something I can do to ensure that this is a correct answer? Yeah, take the derivative of it. The derivative of 2/3 t to the 3/2. 3/2 times 2/3 is 1, and I get 1/2, and there it is, t to the 1/2. It's good. You see? I urge you, every time you take an antiderivative, take the derivative of your answer to ensure that you got the right answer. Because you guys are awesome at derivatives. So use that ability to ensure that you get your antiderivatives correct. And this is going to be from 1 to 4. So this is going to be 2/3 times 4 to the 3/2 power minus 2/3 times 1 to the 3/2 power. 4 to the 3/2, that's 2 to the 8, 8 16, so I got 16/3 minus 2/3, so I get 14/3. Okay? This is part A. I'm gonna have you do part C and B in a moment, but tell me, part C, big F of 1, what do you suppose big F of 1 is gonna be equal to?
0.
Why do you say 0 so quickly? Would you do it all in your head or something?
No, there's a rule for that, but I don't remember what it's called.
You guys
Zero
okay?
something.
You guys, there's a rule for that? You guys okay with that? You got the integral from 1 to 1 of rad t dt, and if the integral's from 1 to 1, it's always gonna be 0? So that required no thought, no calculations. I'd like everyone to please do part B right now. Please find me big F of 0. Please do that now. So what you guys get?
Negative 2/3.
How many people got negative 2/3? Okay, yay, good for you guys. Excellent. Negative 2/3. Good. So that's the first thing I had to do, is expose you to the fact that you can have functions that are defined in terms of the integral of a rate equation, you know, that is the integral of some other function. Well, now it's time for us to say, okay, now that I have a function defined as the integral of a rate equation, what would the derivative of that function be? Let me show you. Suppose I had some function, f of x equals the integral from, let's say, 2 to x of t to the third dt. Let's say that was my function where this is my rate equation. Now, I gotta tell you, why don't we call this just x to the third dx? And the answer is they don't like these guys to be the same letter as that guy. And it's just that, it's just convention. I mean, there's no real reason why I couldn't call it x to the third dx, but they don't, but we don't. So this is a dummy variable. If my rate equation was like, you know, x to the third, then I could call this s to the third ds or b to the third db. I mean, what letter I use here doesn't matter. I'm still going to have to take the antiderivative of it and then stick in those bounds. So this is my function, okay? So the next step is, what if I want the derivative of my function? Whoops, derivative with respect to x. That is, what if I want the derivative of this guy? Well, here's what I'd like everyone to do. I'd like everyone to please take the antiderivative of this guy, plug in your bounds, and then take the derivative of that answer. And I want to see what you guys end up getting. Take the antiderivative, plug in the bounds, and then take the derivative of that answer, and let's see what you got. What are you guys getting as your final answer? Well, are you getting this? Did you take the antiderivative of t to the third and then stick in an x and then a big minus sign and stick in the 2? So if someone want to be gutsy, what's the final answer? Abigail says x to the third. How many people got x to the third? Good, because the derivative of 1/4 x to the fourth is x to the third, and the derivative of this constant is 0. Yes, Kev?
What do you want me to write for the answer for 8?
Oh, I know, stupid Mr. Shana didn't change it. So let's just get rid of these two guys, and then put your answer there, and this is a 3-point question. Yeah. Okay. So let me ask, yes, Daniel?
Isn't 2 to the 4th power 16, not 8?
Oh, I don't know. Yeah, sure, 16. Here, just a second. 16.
Because it gets,
Okay, great.
it gets,
So let me ask you guys this first thing. Did you notice what ended up being the relationship between the derivative of the integral of t to the third and the answer? What did you notice?
They have the same exponent.
same exponent.
Yeah, I mean, they look the same. All I did was take this guy and put it in there. Are you okay with that? Okay, here's the next thing I want you to notice. Did it matter what this bound was? I used a bound of 2, but would it matter if that bound was 3 or 4 or 5?
No.
No, you end up getting the same thing. So I need you to see that the derivative and the integral undo each other. When I take the antiderivative, stick in the bounds, and then take the derivative of that, the antiderivative and the derivative are essentially undoing each other. You see? And so there's a lot of books that will prove that this is true first, and then get this guy proven next. And so that's why this is first and that's second. But the fact is, we get our second fundamental theorem of calculus. And the second fundamental theorem of calculus says this very simply: the derivative with respect to x of the integral from a to x of f of t dt ends up just equaling f of x. That's it. The derivative and the integral cancel each other out. And this guy A, can that guy A be any constant?
Yeah.
Sure, because when you take the antiderivative and stick it in and take the derivative of that, that constant goes away anyway. You see? So this guy A is any constant. So now it is time for me to give you a problem to do on your own. Here, let me erase this. Using the second fundamental theorem of calculus, or the first fundamental theorem of calculus, according to our present textbook. Here. What's the antiderivative of 1 to x, the derivative with respect to x of the sine squared of t dt? Please do this now. I'll give you a hint. You cannot take the antiderivative of the sine squared of t. I mean, it actually has no antiderivative. So you're going to have to utilize this second fundamental theorem of calculus. Good luck. I'll give you 30 seconds. Just to make sure you guys understand what the second fundamental theorem of calculus says. Okay, what'd you guys get for the answer?
Sine squared of x.
How many people say sine squared of x? Yay, that's it, that's all there is to it. Sine squared of x, ta-da. It's just reminding you that the derivative and the integral undo each other. Hey, what's the derivative of 5 to x of e to the x squared d, oops, I made that mistake. You're not allowed to use x. E to the b squared db. What's that going to be? How many people say e to the x squared? Yeah, that's it. That's all that fundamental theorem of calculus is telling you, that the derivative undoes the integral. But there's something I need to make clear to you. This ends up being true only if this guy is identical to that guy. Okay? Only if you're taking the derivative with respect to a variable that is literally the upper bound of the integral. Okay? Only true if these guys are identical. It's only true if this guy is identically the same as that guy. If they're not, then you're going to have to use some cleverness, and that's the next thing I'm going to have to teach you guys.
Are you and your brother identical or fraternal?
I think we're fraternal, but it's not clear. We were born long enough ago that it's not entirely certain what we are, but I think we're fraternal, even though we look and act very similar. Okay, let me give you guys this one. The derivative with respect to x of the integral from x to 4 of, I don't know, the log natural of x quantity to the third, oops, I keep doing that. Log natural of t dt. Does anyone have any ideas? What's this guy gonna end up equaling?
0?
Omar, are you smart today or something? Are you just gonna look at me totally? Oh, Omar says it's just going to be the negative log natural of t to the third power. How many people agree with Omar? Wow, how'd you know, Omar?
Because before it was that minus 0, but now it's 0 minus that.
Good for you. Omar says before it was that minus 0, now it's going to be 0 minus that, so it's going to be negative, yeah? Or we learned another formula, one of our rules of integrals is when you switch the bounds, you just take the opposite of the integral. So this ends up being the negative of the integral from 4 to x of log natural of t. You see that? When I switch the bounds, I get the negative in the integral, and then a constant can come out. So this is just going to be the negative of the derivative of the integral from 4 to x of the log natural of t third dt. And so you end up with negative log natural of x to the third power. Yeah. So I just want you to know, if they switch the bounds on you, that fundamental theorem of calculus still applies. You're just going to have to get the opposite of it. I'm so sorry. Here comes the next one. What if I gave you this? What if I wanted, what if big F of x equaled the integral from 4 to x squared of t to the third power dt? And so I wanted an expression for f prime of x. What do you suppose the answer is going to be now? What's that? Okay, x to the fifth. Cool. How'd you get x to the fifth?
Asking for the derivative of the integral, so x squared raised to the third power is x to the fifth.
Okay, now x squared to the third power is x to the sixth.
Oh wait, oh yeah, that's anyway.
Okay, so Abigail says x to the sixth. Abigail says, hey, Mr. Shannon, just stick x squared in there. Before we were sticking x in, right? Before we stuck x in, now we're going to stick x squared in, x to the sixth. How many people agree with her? Okay, thank you, Omar. A couple of you. Then here's what I'd like you to do. Please take the antiderivative, plug in the bounds, and take the derivative of that. And let me see if you actually get x to the sixth. Are you guys getting x to the sixth? Is Abigail, what do you call it, predicted? Or what are you guys getting? Is anyone here getting 2x to the seventh? Okay, great. So she was close, you know. I mean, there's her x to the sixth. Unfortunately, she's off by 2x. She was off by 2x. She was right to stick the x squared in, but oh, too bad. You had to multiply by 2x. Where do you suppose that 2x came from? Yes, Daniel?
Derivative of x squared.
Yeah, derivative of x squared. And so I want to show you a different version. I'm going to prove it to you later. We've only got 7 minutes left, and I want to make sure you do some problems, because there's a proof of this, and it's by using the chain rule. And I'm going to show you that tomorrow. But I want you to see that the derivative with respect to x of the integral from a to f of x, right? Or maybe I'll call it g of x. G of x of f of t dt, okay? You still stick that in just as Abigail recommended. This is still going to be f of g of x, except you have to multiply by the derivative of that bound. You see? Just like what happened here. Yeah, you stick the x squared in, but then you have to multiply by the derivative of the bound of the x squared. So let me have you do a problem. You know this Xerox that I passed out? Do me a favor and do part E. Do E, and please do not take the antiderivative, plug it in, and take the derivative. I want you to do part E just using this. Let me see if you guys get that. Maybe I should have had you do F. Not too late. Do E. I hope everyone's just sticking 4x to the third in for each t. You don't have to simplify, just stick it in. All right. Hey, 4x to the third minus 4x to the third. Did everyone here successfully stick 4x to the third for each one of those t's? Well, that's what you should have done.
Oh, yeah.
Okay, and then what am I going to have to multiply by?
12x squared.
Everybody thinking 12x squared? The derivative of that guy? All right, so that's it. That's what happens when your upper bound is not an x. If your upper bound is something else, then you're just going to stick that something else in, but remember to multiply by the derivative of that something else. Here's the last thing I want to show you. What if you want the derivative with respect to x of the integral of h of x to g of x f of t dt? Okay? Well, I'm going to show, well, what do you suppose, knowing now what you know about integrals, what do you think I'm going to end up having to do here? What do you think this is going to end up equaling?
G of x minus h of x.
Good, but not just g of x minus h of x. What am I going to have to do?
You're gonna have to evaluate.
Good, evaluate it, which means I'm just going to plug it in, right? So I'm going to have f of g of x, correct? I just plug this in, and then minus f of h of x. Are you guys okay with that? I'm essentially treating it just like we treated integrals, except what do you suppose I'm going to have to multiply this guy by? Yeah, thank you very much, Kylie. Yeah, the derivative g prime of x, and what am I going to multiply this guy by? Yeah, h prime of x. I now want to show you why this is so, or maybe I'll have you do a problem like this first, and then I'll show you why it's so. Here, do this incredibly simple problem. We got the integral of x squared to x to the third of sine squared of t dt. Go ahead and get me the derivative of that integral. And then I'm going to show you why it happens, and then evaluating, and then you will live your lives. That chain rule thing I'm going to have to show you tomorrow. That's really important. All right, happy students. What's this first term going to be? Sine squared of what? Cubed. Good, x cubed, but then what am I going to have to multiply by? Good. And then minus, what's the next one?
Sin x squared.
It's x squared and then multiply by?
2x.
How many people got that right? Okay, beautiful. Most of you, I just want to tell the video audience, most of you got it right. So let me just show you why this happens. I end up splitting up the integral. I end up going, okay, I'm going to go from x to, let's say, 2 of sine squared t dt, and then add that to the integral from, I'm sorry, wait, that's x squared. And then do the integral from 2 to x to the third of sine squared t dt. Are you okay that I split up my integral using one of our rules? That if I do the integral from bump to 2, and then from 2 to bump, that's the same as the integral from that to there? Okay, and then one last thing, I'm going to flip these ones. So I get the integral with respect to x of the negative of the integral from 2 to x squared of sine t dt plus the integral from 2 to the x to the third of sine squared t dt. Then I hope you see that when I take the derivative, this guy's the positive guy and this guy's the negative guy. That's what's happening there. Okay, turn it off. Thanks.